Well, thank you very much for all the presentation, all those answers. There's a lot more questions for a variety of folks, so I'm just gonna go through a printout that I have of the chat so far, and also encourage people to continue asking questions in the chat. And definitely in the chat, remember to say who you're asking that question to. So I have a question from Kevin McLean for Dylan. The question is, can ash be similarly used to raise the pH of urine?
Yes, so ash can be used. The team from SLU in Uppsala in Sweden do that. The main difference with using calcium hydroxide and ash is the saturation pH that you would achieve. So calcium hydroxide would be about a pH of 12.5, and if you use ash, you're looking at about a pH of 10 or so. Yeah.
But that's still effective, it sounds like you're saying?
Yes, yes, it's still effective.
Great. Question for Brandon from Patel Asfaq. Question was, pH at 9 to 10. Struvite might foul the resin. What's your opinion?
Yeah, that's a great question. I think the key there is that struvite contains magnesium, and if you have a separate container before hydrolyzed urine would go to a resin column, that container could allow for the natural hydrolysis process, and upwards of 99% of magnesium is precipitated out during that process. So I don't see a huge concern with struvite entering the ion exchange column to foul the resin, but if it were, that would be something to design around. But I don't see it as a huge issue at the moment.
Great. A question for Daniela. Is there an implication here that if we add acids such as vinegar to stored urine with the purpose of reducing odor, that we could also be favoring E. coli? From Tatiana Schreiber.
Yes, so that was one of our results. And unfortunately that brings the most risk to those handling the urine when it's fresh and when you're adding the acid in the beginning of collection. And so the biggest implication there is that we need to be able to provide a safe working environment for the maintenance staff or for those that are handling urine if we're adding acid. And so once the urine is in a bigger vessel, allowed to increase naturally, the E. coli then, so E. coli to pH, it has 100-fold decrease in concentration at pH of 8. And so as it increases pH, the E. coli will die off, and then it would be a safer liquid solution to handle. But can you stop me? Yeah, the biggest risk is at the beginning of collection.
Another question for you, Daniela, from Sean Schaffner. How do these fecal bacteria samples compare with the other places we see articles come out about, bar peanuts, cell phones, etc.?
I'm sure that they're the same types of bacteria that we find everywhere in the environment. It's very interesting to see that wherever you collect these types of samples, there does seem to be this rising number, like this bacterial community that rises out of the minutia, and it happens to be very similar because of the way that we live in our lives. And so we'll touch things with our hands that are dirty from other things in our bodies, and so things just end up being very similar across the board. But yeah, I mean, I don't know the concentrations. I don't know whether bar peanuts have a higher concentration of bacteria than the urine that we collect. I'm going to say no, but that's just a guess.
Great, thank you. I hope that's true. So let's see, there are a few questions for Dylan around the urease inhibition, the urea stabilization, and then also questions around the biobricks. Let me stick to the urease inhibition first, but we'll also ask you some biobrick questions. This question is from Stephen Vanek. Is there a more homebrew version of that research plexiglass? Oh, I'm sorry, I guess I'm jumping into the biobricks. a more homebrew version of that plexiglass brick that you showed, perhaps a plastic gallon container with sand and calcium carbonate. I'm thrilled to see that and then mentioned that, that they also stored urine in a cooking oil wholesale container, 20 liters or so, with some precipitation, and got that same change to a sweet smell with some lingering ammonia as well.
So to answer the question, the process we use to actually grow the biobricks is rather simple, right? You just have that type of bacteria, you add a urea source and some kind of aggregate, whether it's sand or any kind of loose material, you'll eventually get a solid forming. So in theory, you would be able to do that in a plastic gallon container. Actually, when we first grew the biobrick, we had a team of architecture students from Germany who contacted us, and we helped them grow a sand sculpture, basically, using bacteria and a sand. So it was essentially a face that they grew out of sand. So I don't see why not.
Mm-hmm. Great. We have a couple of questions about the purpose of the bricks. One of them is asking, what is the utility of binding N and P in a solid brick form? Another person is speculating that it could be used for, use the brick as transport and then pulverize it and add it to soil. Wondering if that's one of your intended purposes and what other purposes might be.
So regarding the N and P, the process we develop, we remove the phosphorus first as calcium phosphate. So the actual biobrick has no phosphorus in it. And then in terms of the nitrogen, we break down the nitrogen. So we break down the urea to form the carbonate ion. And the waste product from the biobrick would be rich in ammonium. So you could, if you wanted to, I guess, produce something like ammonium sulfate, which would be another fertilizer. So in terms of a holistic approach, you would have this integrated process producing multiple products. Remind me what the second question was?
It was if it would be pulverized and added to soil, and then what other purposes there might be.
So, I mean, the thinking with this is we just wanted to show proof of concept that you could make a biobrick. You can actually use it for a wide range of applications. You can make biotowels. We are also looking at a way to prevent dust formation on mining dumps. So you create a biocrust over the mine dumps and you prevent that hazardous dust from going into the local communities. So that project is with Anglo Gold Ashanti, which is a mining company in South Africa. So there's a lot of applications. I haven't thought about pulverizing it and using it for soil. But yeah, the focus at the moment, I think that might be a loss in terms of the potential use, because it has the same fulfillment as any other brick that you would make. It actually, the current bricks that we produce are stronger than clay bricks. So we're sitting at 16 megapascals. And the very first brick we made was 2.7 megapascals. So in the space of a year, we've exponentially increased the strength. And we haven't even optimized the process. So I think we could even go higher. So there's a lot of applications.
That was another question I was about to ask you, but you answered it before I could even ask it. Thank you. A question for Daniela came in just now. Have you come up with a good urinal for females?
No, unfortunately, no. So the way that our studies have been designed is to just focus on just male urinals. It is the easiest way to implement urine diversion in the United States right now, because non-water urinals are already approved by the plumbing code. There's a presentation.
So I'm afraid Daniela froze a moment, but she's back.
Yeah.
But anyone who's interested in urinals that work for women, which I hope is everybody interested in that, there will be a presentation on that later on in the summit. I'm not sure in this afternoon in the next session. So stay tuned for that.
Very exciting.
Yes, absolutely. Let's see. So we've got, hard to sort through all the chats here. More questions for Daniela. This one is from Rebecca Nelson. Do the bacteria come from the toilet plume, assuming the mobile urinal has been used in a bathroom facility?
Yeah, so the bathroom that we place the urinal in has 3 toilets and 2 urinals. And so the toilet plume, which was an idea that that recently just became talked about a lot in the news, was because of COVID. But the toilet plume is where we think the fecal contamination is coming from. And so these toilets are flushed with these very high pressure flushers that just bring up a lot of aerosols, and that's how we think the fecal contamination was introduced.
That's very interesting. Great. So then getting back to Dylan with a question, where did it go? Here it is. What is the state of policy on the use of urine fertilizer for crop produced in South Africa? That's from Sharon Majeri.
That's a bit of a sore topic, as I'm sure it's true in most countries. In South Africa, it's treated as a hazardous waste until proven otherwise. So we have to change the legislation if we want to actually commercialize any urine-derived products. Fortunately, we do have the Water Research Commission, which is a local funding organization that is heavily involved in trying to lobby and change that. So I'm hoping in the next few years that we would have that changed as a law, which would then open up the economy to that kind of field where you look at basically value-added products from urine. Yeah.
When you, in your presentation, when you mentioned a building that with urinals in it, collection tank use on a field, is that an existing building or is that a plan?
No, so that's an existing building, and the way they get around the legislation is they don't sell it. They don't sell the, so they just collect the urine and then they put it on the sports fields. And so, yeah, that's a roundabout way with this law that we have. Yeah.
Great. Okay. Let's see. We've still got a few more here and there. Let's see. Getting back to Daniela, what if you had taken sterile samples, maybe an alcohol wipe beforehand, e.g., urine samples taken at a doctor's office? That's from Claudia Lewis.
Yeah. So some of that research has been done in the past. We didn't want to interfere too much with how urine would be collected in the real world. And so that's why we did not sterilize pretty much anything in our study, except for we did sterilize a glass urinal between experiments, but that's pretty much it.
Okay, and I'm seeing I have a question for Nabuya, which was answered perhaps by another person, but I want to pose it to you in case you have more elaboration you want to give. The question is from Nick at Leapfrog, and it's, what material is the membrane made of? And I would add to that, if you could couch that in terms for people who don't know a lot about membranes like me, what's the specific nature of that membrane that makes it work in this application?
So for the ammonia recovery, which is for using membrane distillation, we use a hydrophobic membrane, the Salamian AMV, and then for the DD, we use an ion exchange membrane. So we were exchanging or recovering the phosphate, which is a charged species. So our membranes are also charged in that sense.
Great, thank you. And then another question for Dylan that I want to piggyback on. This is from Hilda Menge. How much calcium hydroxide is needed for 50 gallons of urine? And then I want to add on to that question of, is there any agitation required? I know in your first paper on this, you recommended mixing, but in this presentation now, it looked like it was more passive, perhaps.
Yeah, so those are good questions. So they sent me a private message. I quickly just did the conversions because we work in kilograms. So you would require 1.89 kgs of calcium hydroxide for 50 gallons. Yeah. And then regarding the agitation, so the device we have, we manually mix it at least once in a 24-hour period. So the next version of our urinal will incorporate a mixing mechanism. Yeah. So we found that as long as you mix probably for as quick as 30 seconds in a 24-hour period, you can ensure your pH of your solution is constantly above 12, which ensures you don't lose your urea.
Great. Well, I think we're getting down to the last couple of questions. One here is from Patel Asfak to Daniela. It begins, adding a carbonaceous source for the stability of urine is a very good organic source for microorganisms. Wouldn't that affect the quality of fertilizer produced from the urine due to the population of the microorganism?
Yes, so the microorganisms, if they do grow into a big community, can take up some of the nutrients that we're trying to recover. So that's something that is something you'd want to consider when implementing this type of urea hydrolysis inhibition. But we went into the study thinking that that's why we wanted to study the microbes, but we did not find that they inhibited the amount of nutrients that we were able to recover at the end. So, so it depends. There could be a condition at which you are creating this very rich source for bacteria to grow in, and then to take up the nutrients that you're trying to get. So there is a balance.
Great. I will read a question. It's a general question to everyone on the topic of toilet plumes. Has anyone thought about using the concern regarding the toilet plume to help push policy, design, and manufacturing toward improved waterless toilets for both public and private restrooms? And I think that might be a good one to just end on. And anyone who's presented can answer that, and anyone who is in the participant who has not been presenting, I think we'll transition into the break time and just leave the room open. So this can be an open discussion between anyone who has ideas. So again, the question is can we use the concern around toilet plumes to drive these advances that we're hoping to encourage?
In terms of the plume, I think I was just going to add to the question, which is some of the kind of recent COVID-19 toilet-related kind of dialogue that's going on can help, I suspect, contribute to the discussion around policies pushing towards more waterless devices. But I would say, also I want to say, COVID's the least of our worries, I think, when it comes to toilet splashing. It's other agents more so, but I think in today's time, it's an opportunity to move that conversation forward.
Great. Well, let's segue now to the breakout rooms. And thank you very much to all the fantastic presenters today.
Thank you.